Hey folks, okay, this time around I want to talk about working with text in C and C++, and in particular I want to look at how that's typically represented sort of behind the scenes. So it seems fairly natural if we're displaying a bunch of text to the user, or if we're reading a bunch of text that the user is providing for us, that we store it as an array of characters. Right? So we've got, we want somebody to enter their name. We have an array of characters that's hopefully big enough to hold their name, and we read their name into it. Now this kind of thing is done all the time, right? Working with text is really common. And so by convention, C and C++ programmers have pretty much agreed to use this one special technique for working with arrays of characters. Not for other kinds of arrays, but for arrays of characters. And the idea is we need to create an array that's big enough for whatever text we're getting the user to supply or whatever text we're producing. So say we're going to get them to enter their name. Maybe we pick 256. We'll create an array of 256 characters, get them to enter their name, and we'll store it in there. Now, when we want to work with their name, we want to print it out or something like that, then we need to know where in the array it is, because it probably doesn't take up the whole 256 characters of the array. So by convention, what we decide is we'll put it at the beginning of the array, and then somehow we'll have a marker that says, okay, here's where their name ends. So if they type in Bob, then it's the first three characters of the array, and then there's this marker saying, okay, that's all that we used at the moment, right? The rest of the array is just kind of garbage for the moment. So we need to agree on what we're going to use as a marker, and we kind of want it to be something that wouldn't be typed in normally. So we don't want to use X or Q or an exclamation mark or something like that, because those are all things that we would want to include as part of our text. So what we'll look at today are the conventions that have been agreed on for working with character arrays in this way, and some of the functions and routines that support them. So that's the plan. We'll see how we go here. So the first thing I really want to stress is, again, this is only for arrays of characters. The techniques that we're looking at here have been adopted for working with arrays of characters, not for any other kind of array. So the things we do here won't work on arrays of ints or arrays of floats or arrays of anything else, just arrays of characters. So we need to come up with an agreement on what we'll use as this special marker character saying this is the end of the useful chunk of the array. Well, in C and C++, each character is actually, so a character variable or a character in an array is represented using a single byte of memory someplace. And in that byte of memory, there's an integer value stored. And it's got to be a small integer because it's only got one byte to fit in. And so we're actually just going to work with values from 0 to 127. So 128 possible values in there. And each of those integer values represents one specific character. So again, there's an agreed mapping of which values represent which characters. So this mapping that we're interested in is called ASCII. And we can take a look at the ASCII table. So this is, you want to Google it, you'll find tons of different copies of the ASCII table floating around. And so this goes through and says, for each integer value, so from 0 to 127, what character does it represent? Now, there's a bunch of other information that's given in this particular table. It's got the representation in base 10, the representation in hexadecimal base 16, the representation in octal in base 8, because these can come up in different circumstances. They're a relevant way to look up the information. For the moment, we'll just focus on the decimal value. So for each of these, you've got a decimal value and then a description of which character it represents over on the right-hand side there. So for instance, the space, if you hit the space bar, is represented by the ASCII value 32. The character 0, right, the digit 0, if you typed it on the keyboard, is represented by the value 48. The uppercase A is represented by a 65. The lowercase a is represented by a 97. So you've got these 128 different characters that we can represent, and each of them has a unique value associated with it. Now, if you have a look at this table, browse through it at some point if you want to, the ones that we can type start around here, start around the 32, and then you'll see punctuation and digits and more punctuation and uppercase letters and more punctuation and lowercase letters and more punctuation. So essentially the things that we can type go from 32 up to 127. The stuff below 32 represents a variety of different special control characters. And again, you can have a boo through these. A lot of these have kind of historical roots, but aren't things that we work with a whole lot, or that we're not going to work with in this course a whole lot. But the one that we are interested in is the very first one, the one with ASCII value 0, the null. This is something that you can't type on the keyboard, right? It's something that isn't a printable character. It's not one of the various printable characters that we can actually see out, for instance. But it's going to be useful to us in that this one, the 0, the null, is the one we're going to use as the marker, simply because it's not going to get used for actual storing user text. So this is the value that we've chosen. This is the value that we're going to work with. Now, in fact, if you want to play with the conversion back and forth between ASCII values and the characters they represent, we can do that in our programs as well. Let's have a quick play with that, and I'll just show you some of the ways of going back and forth between these things. So here's a little program, and I'm just going to use cin and cout for this one, where we're going to store ASCII values in character variables, or store values in character variables using the ASCII, and then we'll do some conversions back and forth. So one of the things I can do is I can specify a character in single quotes, but using its ASCII code. Now this X indicates that I'm using the hexadecimal representation. So I use the single quote, the backslash, the X for hexadecimal, and then the hexadecimal value that I want. And so if we take a look back in that table that we had a second ago, if we look under the hexadecimal column here for a 41, what's a 41? Here it is. 41 in hex is the uppercase A. And actually, if you have a look in the table, hex 41 is decimal 65, right? That's our character A, character uppercase A. So, in theory, if we do this, if we print out our if we store using the hex value 41, the decimal value 65, store a value in a character, when we go to print it out, right, we'll print out the hex for it, we'll print out the ASCII value, which is going to be our 65, and we'll print out the character, which should come out as an A. And then just to show again, I can actually assign integer values to character variables, and it will assume that what I'm using here is the ASCII value. So if I assign 65 to character variable C, it thinks I'm saying, okay, well, find the character with ASCII value 65 and put that in here. And again, what we'll do is print out the ASCII value, and we'll print out the character. And so we should be seeing these 65s and A's coming out when we run this. And then maybe we'll go a step further and get the user to enter a character, so they can enter any typable character they want. And we'll show them the character and show them the ASCII code that matches that. And then we'll take it one step further and say, enter an integer for an ASCII code. We'll show you the code, and then we'll show you the character that matches up to that. So we'll just give this a quick try. Let's see if we can compile this beastie. And then we'll try running it. And so back in those first two lines that we were looking at, it's actually telling us, okay, what you gave me, that hex 41, is ASCII value 65 in decimal, and it represents character A. And then we had it the two ways, where we actually assigned the hex 41 and where we assigned the integer value 65. And in both cases, saying, okay, yeah, if that's the ASCII code you want, here's the character it represents. And then we can say things like enter a char. So let's enter an uppercase B. And this comes right after the A in the ASCII table, so hopefully this one's got ASCII 66. And sure enough. And again, we can go the other way around. If it asks me to enter an integer, so I enter a 66, say, it's going to give me back the B. right? Or if we try this with other things and I enter an exclamation mark as my character, that's got ASCII code 33, right? Or if I enter an integer, let's say I enter the 32, that's the one for a space. So again, in here it's showing me the character between single quotes, and it's showing that I've got the space in there. So we can go back and forth in our programs if we want to, from ASCII values to characters and the other way. So this is what we'll have a boo with. And so again, for our null terminator, for our special marker, which is where we're starting with all this, we're going to use the one with the ASCII value 0. So that \0 as the representation of the character with ASCII value 0, this null. So that's what we're going to play with here. We're going to, every time we use one of these functions to work with arrays of characters, we'll be throwing in this null terminator at the end of the chunk that we're interested in. So a lot of functions have already been built with that in mind. cin and scanf will work this way. So cin and scanf, if we try and read text from the user, will each read in the text and then put a \0 in the next space right after the text. So they're putting it in there for us. So let's say we create a character array of whatever name you want and whatever size you like. If you do a scanf and then %s is the format character for our format string for text for character sequences, and then the name of the array. And note that we don't have the ampersand in there for our character arrays, it's just the name. So this is going to use the usual scanf kind of idea where it skips any leading white space and then grabs the next blob of stuff that isn't white space and puts it in the array and then puts a \0 right afterwards. Same idea for cin, right? If I say cin and then into some array, it'll skip any white space that the user types first and then read the next blob of things that don't contain white space and put that in the array and then put a \0 right afterwards. Now this is a little risky in that these things don't check to see if the user types in too much. If we've got an array of size 10 and the user types in 20 characters, it's going to go off the end of the array and right into memory someplace else. But we'll deal with that a little later on. And then we've got the ability, if we want to get the white space, so if we ask the user to type in a sentence or something like that, we don't want just one word, we want to get the whole line that they type in. So both libraries provide a way for us to do this. The cstdio library gives us a function called fgetS, where we give it the array, the maximum size to read in, and we tell it where to read from. So for reading from the keyboard, the keyword for that is stdin for standard input. Later on, when we talk about file I/O, we'll be able to specify a way for it to get information from files instead. So this will read in an entire line of text up to the maximum size or where the user hits enter and store it in our array. And again, it will put a \0 at the end of the line. IOStream, again, provides a similar idea. It's called getLine. And again, we tell it where to read from, so cin when we're reading from the keyboard, for instance, and the name of the array to put it in. Oops, that should have been a text with an E there. Right, putting it in the same array. And same idea, it reads into the array and puts the \0 in at the end. So we've got these input routines that will allow us to read text from the user, store it in a character array, and essentially read a whole sequence of characters into the array for us. So again, usually with arrays we can't do that. We can't fill multiple parts of the array at once. But character arrays are a special case here, and it's just because the functions have been written to work with this idea of the null terminator. So we can do input, and then the output routines work pretty similarly. Oh, sorry. We can actually also go through and get just a single character at a time as well. So there's a routine called getC that reads just one character, but if we do want to capture white space, if the user types in a space, it will get that. So this one doesn't skip white space. And again, that's in the cstdio. And similarly in IOStream, if we want to get a character but not skip white space, we can do that with the no skip white space keyword. So we've got a couple of options again for grabbing things without skipping the white space. All right, the other thing I wanted to mention was output. And again, the output functions assume that that null terminator is in place so that it knows where to stop printing things out. So if I go through and use cout and an array name, and again, presumably this is a character array, it will print everything in the array that it sees before the null terminator. So it stops when it sees that null and doesn't print that. Same thing with printf, right? We use the printf %s and then the name of our array, and it will print everything in the array prior to one of these null terminators. Now again, there's a bit of a risk here in that if somehow we've messed up and we haven't put a null terminator inside the array, then the cout or the printf will go printing right off the end of the array and printing whatever's next in memory until it just happens to stumble across some place where there's a null in a byte of memory. So these are things that we have to worry about, but we'll play with those later. Let's maybe just take again a quick example of a bit of programming with this kind of an idea. Let's see, did I put this in null string? No, I didn't. Okay, let's write our own example here. So let's do something like string.io.cpp, and we'll just do the IOStream version here. So using namespace standard, and again, we'll create our character array. And you can call it anything you like. I'm just going to keep using size here, although I should probably define size, shouldn't I? How about we do const int size, and I'm going to keep this small for the moment. And we'll tell the user, you know, please enter a word. We'll read it in. Oops. And we'll print it out. You entered and so we'll compile it and see if I've got any errors in there. And I do. Oops. Should have used my array name there. So we'll use cin to read into the array, and we'll use cout to print the array contents. And that looks a little better. So we try running it, asks me to enter a word. Now again, just to show that this skips white space at the beginning, I'll throw in some white space, and I'll say, you know, blah, 9, exclamation mark. And again, all of this stuff it's going to read in as part of the word, right? Everything before it sees more white space. So then maybe I'll throw in, you know, a little more white space and hit enter. And it shows me what it read in, right? Everything that skipped the white space, and then read everything that was before where the white space started again. So we can go through and use this stuff to read words at a time. Or again, if we want to try something with a line of text, let's say, please enter a line of text, and we'll read it in. Oops, we'll use getLine, and it's cin and the place we want to store it. I'm going to make my size bigger here so that I can actually type in something a little bit longer. And we'll compile. Oopsie, what have I done? Have I messed up my get line? Looks like it should be okay. One moment while I pause and debug. Well, that was exciting. I totally blew my syntax there. Apparently I'm way too rusty on doing this with cin. So the idea is for cin, the getLine is actually part of our a method within our cin class, and we provided the array and the maximum size to read in. So I totally blew the syntax for that. I'm going to have to go back and correct my slides. So it's cin dot and get line and the name of our array and the maximum size. So this provides a safeguard in that we're not going to run off the end of the array as long as we give it a valid size here. So we can go through and get a line of text this time. And so let's try compiling the beastie. And somewhere in here, where did my, there we are. We'll try running it. Please enter a word. So that's our old one. And then please enter a line of, oh, of course. So the get line reads everything up to a new line, and so I've got a it reads everything up to a new line. I've got a new line sitting after the text, right? I typed in foo and then I hit enter, and so that first cin read in the foo but left the enter sitting there, the new line sitting there. And so when it grabbed this second one, it grabbed the new line and figured I entered a line of text that was just a new line. So let me just demonstrate this. We'll take that first word out here and compile again. So please enter a line of text, and so I'm going to throw in some spaces, blah, 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 foo, exclamation mark, maybe a few more spaces, and then we'll hit our enter. And did I not print it out? I didn't print it out afterwards. How about I print it out afterwards? You entered, and we'll put a single quote before and after the line of text. So let's try that one more time. How about some spaces, blah, 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 some spaces, and we'll hit enter. And there we go. You entered, and you can see it grabbed the whole line, grabbed the spaces, grabbed the blah, 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 grabbed the spaces, and then stopped before the new line character itself. So we can go through and get lines of text if we want. We can get individual words if we want. We can get individual characters if we want. Lots of different options for playing with our input and output. Now, all of this is based on the notion that we're putting this null terminator in when we put the content into the array, and we're using that as an indication of when we should stop when we're using the array later on. Now, we can quite happily do this manually. You know, I can go through and stick a bunch of characters in an array and then manually put a \0 in afterwards, a null terminator in afterwards, and then if I cout it, it's going to print everything, again, prior to that null terminator. So in this case, I've got my AB space X and then a null terminator. So if I cout it, it's going to print the AB space X and then stops before the null terminator. If I put a null terminator in the very first spot and I try and cout the array, it assumes that this is essentially an empty string, right? It's saying I'm going to print everything before the null terminator. Oh, the null terminator is the very first thing. You don't want me to print anything. Alrighty. Now, a couple more interesting bits and pieces with characters. ++ and -— work on our characters as well. So it will go through and assume that you want to add 1 to whatever that ASCII value is for the character. And so if you do something like assign, character A to a character variable, and then do a ++, it's moving to the next character in the sequence. So now it's moving on to B. Or if we did a --, it would move to whichever character was right before A in the ASCII table. So what's right before A in the ASCII table? Right before the lowercase a is the backtick. So again, you can move through forward and backward using ++ and -. So if we were to, again, just play with a quickie example of that. Let's see, I think this is our null string.cpp. So in here, we've just got an example of a loop that's going to go through, and we're going to start with character A, and we've got an array of size 11, And I'm just going to have a loop that goes through 10 values, right? It's going to add the current character to the array in the current position. So it's going to put A in position 0, and then add 1 to the character. So that's going to go on to B, and add 1 to the position. So it's going to step through the array. And in theory, this should be putting A, then B, then C, then D, etc. in the spots in the array. And then when it dumps out, it'll put a \0 in the position right after the last one we used. So in position 10, it should be putting our \0, and we'll print it out. And hopefully we get our A through I or A through J or whatever our first 10 characters are. So let's do our, we'll compile our null string.cpp. And try running the beastie. And sure enough, we get our first 10 characters, right? Our A through J. And we're done. So you can use the pluses and minuses. You can also use comparisons between characters. And the comparisons are done based on the ASCII value. So if I've got characters in 2 variables and I do if one's less than the other, it just does that based on those ASCII values. So these things do become relevant when we're comparing things as well. Alrighty. Now, the cstring library provides us with a whole slew of different functions that work on the assumption that our character arrays are null terminated. So here we've got a function called, well, string length, strlen. We pass it a character array that hopefully has the null terminator in there, and it counts the number of characters before that null terminator. So if we've got 10 characters and then a null, this is going to return 10. Strncpy, so the strcpy, takes 2 character arrays, copies the second one into the first one, but again, just up to that null terminator. Strncat is for concatenation, and so what that does is takes whatever's in string 2 and copies it onto the end of whatever's in string 1. So you get the old contents of string 1 followed by the contents of string 2 and then the null. And then there's versions of each as well that let you specify a maximum size so you don't overflow your string 1 when you're doing this. So there are a whole slew of different cstring libraries provided that allow us to play with this kind of thing. So again, here we've got an example where we're going to go through, create a couple of arrays. We'll get the user to enter 2 names. We'll put one in the first name, one in the second name, and then we'll build a full name in a third array here. So we can get them to C in their first name, get them to C in their second name, and we'll put those in the 2 arrays. And then we use that string copy to say, okay, copy the contents of name 1 into the big array, if you like, into the full name array. And then we're going to do strncat to say, okay, after the first name that's in full name, put a comma and a space. So we're saying copy this string here, the comma space, onto the end of whatever the name was that we put in full name. And each of these things is looking at where the null terminator was and then moving it appropriately. And then so we'll do the same thing with the second name. We'll say, okay, well, let's copy whatever was in the second name onto the end of our whatever's in full name. So now we've got the first name, a comma space, and the second name, and then a null terminator. And so if they'd entered Scoobert and Do for our 2 names here, then what's coming out is the Scoobert, and then a comma space, and then a Do, and then \0. And again, if we do a string length on this, this is going to go through and count the number of characters. So hopefully I counted correctly, and there should be 13 characters in there before the null terminator. So it counts every character in there, it counts any digits that are there, any punctuation that's there, any spaces, right? It counts everything in there prior to the null terminator. So we can play with lots of things. Oh, I didn't mention string compare. That's another interesting one where we can go through and compare 2 strings more or less alphabetically. So let's have a quick play with that. So let's try. I don't know, we'll call this comparison. So again, I'm going to use my, I'm going to use my iostream library, and I'm going to use this cstring library And we'll use our namespace standard for the IOStream stuff. And what we'll do is this same sort of idea where we'll have a couple of character arrays. So I'm just going to call them text1 and text2. And once again, I should probably declare my size here. So I'll create my couple of character arrays, and I'll get the user to enter 2 words. And I'll read them into text1 and text2. And then I'm going to compare the two of them and see which one should come first. So the function that does this is called strncmp, strcmp, and I give it the 2 arrays. And there's 3 possibilities. This is going to return an integer value that's either positive, negative, or 0. So if it gives a negative value, then I'm going to say text1 comes before text2. Else, if it returns a value that's greater than 0, so this is going to give me a positive value, a negative value, or 0. It's going to give me a 0 if they're the same, and then a positive or negative value based on which of the 2 should come first, kind of alphabetically. So we're just trying to figure out whether text1 or text2 should be first alphabetically. So otherwise, we'll say text1 and text2 are the same. So I just want to go through and play with this string comparison program a bit. So we'll do our compares, throw in our warning flags, and we'll try running this beast. So if I enter foo and blah, then it tells me that blah is alphabetically before foo. And again, we try it the other way around. If we try blah and foo, same thing. It should tell me that blah comes before foo. So of my 2 words, it's doing this comparison and it's telling me which one alphabetically comes first. Now, the thing is, it's using the ASCII characters, the ASCII values to figure out which characters belong first. Now, we can do comparisons like let's say AAAB and AAAC, or no, let's try something like BB. So what this is going to do is go through character by character. It says, oh, the A's are the same, the first A's are the same, second A's are the same, third A's are the same, and then in that 4th character, one of them's got an A and one of them's got a B. So it should tell me that the one with 4 A's comes first. Yeah, so the 4 A's and a B comes before 3 A's and a B. But it is using these ASCII values, so we can, if we say things like AAA and AAA, if you recall in our ASCII table, the uppercase characters came before the lowercase ones. So this one's going to tell us that the uppercase ones come first. And you can throw punctuation in there, so I can say 965 and exclamation mark, question mark, foo. And it's going to tell me which one comes first, but again, it's just based on the ASCII values of those characters. So that's what it uses as the basis for its comparison. So although most of the time we're using this for alphabetic comparison and it works kind of naturally, you do have to be aware of the fact that as far as it's concerned, uppercase letters comes first, and it will happily try and do comparisons between things that aren't letters. So just so you're aware. And there is also a a string n version of this where it compares only a specified number of characters. So if I say text1, text2, and a 4, then it's just going to compare those first 4 characters and see if the things are less than, greater than, or the same up to that point. And so we'll do our comp x. And let's say blah xyz and blah abc. But because it's only looking at the first 4 characters, it's probably going to say they're the same. Right? Yeah, so it's saying they're the same. And again, if I was to do that again and say blah and blob, again, it recognizes the differences between those because it's, you know, the 4 characters are enough for it to see a difference. So you can specify upper limits on how much of this thing to look at, how much of it to use. All right. So I think that was the kind of intro level I wanted to give for our use of these null terminated character arrays, and a bit of an intro to our string copies, string concatenations, that kind of thing. Again, we'll make use of these libraries a fair bit. What I want to do in our next session is to get into the C++ string class, which kind of puts an even nicer wrapper around all of these things and makes using some of this a little bit more intuitive as well. But behind the scenes, it's using things that are very similar to this. Actually, no, I lied. I'm going to do one more thing here. I'm going to take a little bit of a look at how we could do some of these things ourselves. Right? We don't have to rely on the existing routines to provide us with the ability to do copies and that kind of thing. So let's write a quick program, our string or something like that. So in here, what I'm going to do, I'm going to write our own version of string length. So I'm going to call it something a little different, where we give it a character array and a size. Oh no, we don't need a size. We give it a character array and it will return the length. Or maybe another one for, how about our own version of a string and compare. Oops. Where we give it two character arrays and a maximum size, and we'll return -1 if string 1 is before string 2, 0 if they're the same, and +1 if string 1 comes after string 2. Again, pseudo-alphabetically. And again, that's just looking at the first n characters. And so in our main routine, we'll come up with a size, a couple of arrays, oopsie. Sorry, I'm not showing you any of this, am I? How about this? So as I babble away, again, what we're going to do is write one function to go through and compute the length of a string, null terminated, and one function to return a +1, -1, or 0, depending on whether we'll take 2 strings as parameters and see if string 1 should be before string 2, or it should be after string 2, or if they're the same, but only looking at the first n characters. So we'll do our own version of string compare and our own version of string length, just to show that this isn't actually too bad to do. So again, in our main routine, we'll create our couple of arrays. We'll get the user to provide us with 2 words. And read them in. And let's try out our string length, the length of text1 is, and we'll just call our string length on it. So we'll pass it text1, and hopefully this will work. And then for the string compare, we'll do the same sort of thing as we were looking at before. If our strncmp text1, comma text2, let's look at the first 5 characters just for the sake of argument, is 0. I'll say they are the same in first 5 characters. Else, if string compare text1, text2, 5 is less than 0, let's say text1 before text2, and then if they're not the same and text1 should come first, then it should come second. So text1 comes after text2. And again, we're only looking at the first 5 characters there. And the part we're interested in is to actually write these 2 functions. So let's see, for string length, what do I want to do here? Well, I want to go through and count the characters for the null terminator. So I'm going to set my count to 0, and I'm going to say while what's in the string in the current position. So I'm going to use count both as the position in the array that I'm currently on and the number of things I've seen previously. Sorry, when I'm on position 0, I haven't seen anything yet. When I'm on position 1, I've already seen 1 character. When I'm on position 2, I've seen 2 characters. So while the position I'm on does not contain the null, I'll keep going. So I'm just going to keep going through, bumping up my count until eventually I land on one of those null terminators. And then I can return the count when I'm done, right? Because that tells me how many things I saw before the null terminator. So this should go through and give me a correct count of how many characters there were in the word. And then for the string compare, it's a similar idea. So we'll have our, let's call it positions time around. So we'll start at position 0. And while the position is less than n, so we want to keep going kind of until we hit the end of the strings or until they differ in some spot. So if what's in the first string in the current position is less than what's in the second string in the current position, then the first string should come first, right? We've seen, for instance, an A instead of a B. So I'll return a -1. Otherwise, and same sort of idea, if what's in the first string is bigger than what's in the second string in the current position, then I've found the first place where they're different and the thing in A in the first string comes afterwards. So I'll return a 1. And otherwise, they were the same in the current position, so I'll just keep going. Oops, so I want that to be pause. So I'm going to go through and just keep moving along until either I find someplace where they're different and return either a -1 or a +1, or until I hit that limit n. And if I hit that limit n, then they're the same all the way up to n, so I want to return 0. So let's see if this actually works out. Oops. Forgot my dash O. And what have I messed up? I've blown my syntax here someplace. Okay, hang on. Let's take a look at whatever the first error message was there. Blah, 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 blah. Oh, I've got a closing curly bracket, right? It's telling me that it expected closing square bracket on line 45, character 32, and yeah, sure enough, I've got a typo in there. So line 45. So I'm going to go to line 45, and sure enough, there's my typo. And it looks like I've got the same typo just a little further down. So let's try compiling again. And that looks a little better. And enter 2 words. So I'm going to enter blah blah and blah foo. So hopefully, since we're comparing 5 characters in this one, it should actually detect that B and the F are different. So it should tell me that the first word comes first. Blah blah before blah foo. Okay, so let's try it again. And let's do A, B, C, D, E, F, and A, B, C, D, E, G, something like that. But the first 5 characters are the same. So hopefully this tells me that 2 of them are the same. Yeah, they're the same in the first 5 characters. And of course, our length here, as you can see, is going through calculating the length of our first word in each case. And it does look like it's getting the right number of characters for there. So our string length seems to be working. Our string compare seems to be working. Let's try, how about an X and an A, so we'll just have a couple of short words here. And yeah, so it correctly detects that X comes after A. So we can go through and implement our own comparisons, our own version of concatenates, our own version of copies, right? If we want to go through and do something like a our own version of copy for string 1, oops, yeah, string 1 and string 2. Right, we can quite happily go through, and it's a similar sort of idea where we're just going to go through until we see a null. So what I'm going to have is our position is 0, and I'm going to keep copying from string 2 into string 1. So while what's in string 2 in the current position is not our null terminator, we'll go through and copy what's in string 2 in that position into string 1 in that position. Right, so we copy it across and we move on to the next position. And we just keep going, and eventually this will see the null terminator in string 2 and stop. We just have to make sure that we add that null terminator to string 1 as well. And so again, we can go through and quite happily create our own copy routines, and hopefully everything should work out well. All right, I will leave it there. And we'll continue on playing with strings next time around.